Well, yeah, thank you for the opportunity to present this paper here. So this is work that we did a couple of some time ago. Gabriel was my postdoc at that time. Hannes is still my PhD student, and I'm here to give the presentation. All right, so that's interesting. Okay. So this diagram is from the Chromium website, and it gives an overview of difficult bugs that you find there. And the ones that I would like to draw your attention on are the big blue and the big red area, so which is about use after free errors and other memory unsafety. Now, I guess all of you know what language this software is written in. Well, Chrome is written in C and C++, and surely bugs like that only occur in such languages, such low-level languages, and they don't occur in high-level languages, type languages like OCaml, right? Which is what we like to write to write software. But unfortunately, let's try to write some OCaml code. So here, the first line, what we're doing is we're creating a connection with a key value store, which maybe contains some grades or something. Then in the first line here, we are, so which is the magic button? I think this one. Well, right, then we add some record to that. Then we're closing that. And then in the last line here, later in the program, we are using that handle again and trying to find some entry. Well, that's pretty unfortunate because the first stuff will run through, but then on the last line, we get a runtime error. Well, and if you expect me now to speak about type state, no, this is not the solution that we are talking about in this paper. Also, you may have seen me talking about type state too. In this case, what we want to advertise is a, let's say, language extension of OCaml that Gabriel called Affe. And in this in this language, the code looks almost the same up to those little ampersands here. And with that, you suddenly get a compile time error here. And the magic behind that is essentially that we added some notion of linear types. So Affe has a notion of resources. And as we will see later on, you can essentially specify if resources are linear or affine. And then if you actually want to use such a resource, you have to tell in what mode you use it. So essentially what you do is, maybe I should do that more, not that direction. Okay, so, right, so you get resources, which could be linear or affine. And of course, there's the usual unrestricted types, like that. Then, if you want to use them not linearly or more flexible, then you have to explicitly write borrows like the ones here. The difference here is that this one here is a mutable borrow, where you can actually apply mutable operations to it. And this one down here, I mean, with notation which is a little bit inspired by Rust. So this here would create an immutable borrow where you can just observe. So these are borrows, and nevertheless, well, come on. Well, anyway, nevertheless, down here at the close, the linear resource is removed from the scope, which means down here you get a compile time error because this variable is no longer available. So you can't even take the borrow of that anymore. Moreover, and that was one of the design goals, I'll make it this way. You don't need to write any type annotations. So the system comes with complete type inference, and I will later tell you a little bit more about how far that actually goes. Right. So in the rest of the talk, I will go pretty much high level over these four topics. If you still manage to dig out the paper has a lot more detail, technical detail about the type inference algorithm. The type system is, of course, described in detail. And there's also a semantic model and a soundness proof that includes all the structural and memory management properties. Yeah.
Just a clarification that at the beginning of the talk, you motivate with the use of the free bugs in Chrome. But because OCaml is garbage collected, you actually will not get a memory bug per se. But you are talking about in general how to track whether a resource is still available. Right?
Yeah, right. So that's true. But what you can do with this is you can treat an area of memory, an uninitialized area of memory. You can treat that as a linear resource, and then essentially the closed equivalent would be the deallocation of that. So essentially, you can do your own sort of manual management inside of the garbage collected language. So maybe as a side note, one of the motivations to develop this system was that both of us, Gabriel and I, we were kind of unhappy with the standard mode of Rust and other systems where you start out being completely manual. So we sort of come from this functional programming tradition where everything is garbage collected, and everything is automatic. But then there are things that you really want to manipulate manually, and that's the idea of the system. And we want to do that in a way that the properties that we like type inference as much as possible, that they are all preserved. And that's the complete picture, I think. All right. Well, how do we do linearity? We do that by extending the type system with some notion of kinds. And I think it's now reasonably standard. So we have linear kinds with the usual semantics. We have affine kind, which means used at most once. And then there is an unrestricted kind for all the rest, where you can use variables as much as you want. Moreover, kinds, I think it, okay, and down here are some examples. So you can declare types, so you have these extra kind annotations. Moreover, kinds can also be polymorphic, and the type inference mechanism tries to infer kinds as polymorphic as possible. I mean, in the usual principal types way. So here's an example. So you can, for example, define a list with elements of arbitrary kind, and then this kind is inherited by the kind of the elements is kind of inherited by the list spine itself. Then you can write code like this, where you say, I want to create a list, and then I need a value of type A, but A has to be unrestricted, and then you can put that into the list. And of course, it must be unrestricted because the first argument tells you how many times you put it in the list. So you're kind of duplicating it from that end. Moreover, we have the kind of natural subkinding relation, where we say that anything that's unrestricted, we can also treat it as affine, and everything that's affine, we can also treat that as linear. So we have this this lattice of kinds. Right now, the lattice looks a bit impoverished, but actually, in reality, it's a bit richer, and I will briefly hint at that. Yeah.
But linear says use exactly once. But
linear says means exactly once.
But affine includes also.
Affine means you can also drop it. Yeah.
Nice. Okay, it seems like those are contradictory.
No. Why? No.
Because linear says you use it exactly. Oh.
Yeah.
Right, but okay, maybe.
Yeah, I mean, so here, this is like the idea of the consumer, right? This your object says, I can be used in any way you want. And when you do the subkinding, when you subsume the kind, then you're looking from the perspective of the what did I say, consumer? So here you're looking from the perspective of the producer, right? The producer said, well, this is my features. And if you do the subsumption, then you change the perspective and you ask from the side of the consumer, So, and if the consumer says, I'm only treating, I mean, that's a promise, right? I'm only treating you as linear, then you say, okay, do whatever you like. That's the idea. Right. Now, of course, since we have a functional language, we have functions and we have to deal with functions that capture our precious resources somehow. Like here, now we open the database and then we write some sort of function that closes over that. So what happens is, well, it gets captured, okay, as usual. Since this handle to the key value store is linear, this use inside of the closure uses it up, right? Moreover, no, it's in the closure, and we promised to only use this handle linear, so the closure has to inherit that linearity. So the inference will generate a function type, and the function type will then also be tagged as linear. Notice this is different from if you look at a linear type system and you think about the lollipop. So this is not the lollipop. So this type says I'm a function and you can use me. You have to use me once. That's not the meaning of the lollipop. The lollipop says I'm a function. I have an argument and I promise to use the argument exactly once. So this is often confusing in this context. Here, the meaning is really we don't make any promise about the string argument that's here. That can be used in any way whatsoever. Also not about the output. It's just you must use this function exactly once, which is super limiting, of course. Right. Good. Well, let's press on. Yeah.
So suppose you have a function that captures multiple different values, and then you need to choose the most restrictive one, I guess.
Yeah, of course. Yeah, exactly. Yeah. Which would be, if you capture one linear thing, then the function is also linear, which is fine by the subkinding that we just discussed a couple of minutes ago. Right, now to the ampersands. Right, if we have a linear affine resource, for others it doesn't make sense. You could do that, but it doesn't really make sense. Then a borrow is kind of a temporary loan of this reference, and that goes back actually quite some years already. Because just having a linear resource is just too limiting. Sometimes you want to do something to it, and here we have two different borrows, the usual ones. So one is what we call a shared borrow, and they are there for observing the resource, and exclusive borrows for modifying. Right. Now, so this is the correct use of borrows. So here in the first line, we are using shared borrows, and it's okay to use that several times in the same expression. Whereas down here in the last line, and this happens in a particular scope. Whereas down here, we are using an exclusive borrow, and that cannot be shared with another borrow at the same time. And by the way, the borrows themselves, they also get a kind, and the kind of the borrows is different from the kind of the underlying resource. In particular, the shared borrows are unrestricted, so you can just pass them on and duplicate them, but the exclusive borrows, they are affine. So you can take them, you can use them once, or you can also discard them, which is fine because it's only a borrow and the actual resource is still held on somewhere else in some caller or something like that. Right.
Sorry, I have any questions.
Yeah, sure.
Exclusive borrow, is that like if you use it exactly once, is it really a borrow? Are you giving it back, or it's used and it's done?
It's really a borrow in the classical sense. So I'm only so this talks only about the borrow. So this is the notation that kind of creates the borrow and passes it to this function.
But like, isn't the point of having linearity that, or like using things exactly once or at most once, if you can borrow them and mutate them, doesn't that defeat the point of linearity?
That's a good question. So maybe the right answer is that we are using linearity really to enforce some sort of life cycle on resources, mainly in the sense that we want to properly serialize um, modifying excesses, and we want to make sure that at the end the resource is deallocated if it's linear. And if it's not linear, then we can probably just get rid of it without explicit deallocation.
Okay, so it's not linear in the sense of it's a resource, once you consume it, it's gone. It's rather restricting how it's being modified.
So we make the distinction between consuming the resource. If you have an operation that consumes the resource, then it's gone. But in addition to that, like closing the file handle, that is gone. But in addition to that, you also have operations that kind of take a borrow, do some operation, maybe just observe it, or you have operations that also can affect the state, whatever. Mm-hmm. Right. Now, so one rule is that you cannot use the borrow and the resource itself at the same time. So why is that? Suppose you were sending the resource and any borrow to a function, you wouldn't know. If you pass on the resource, which you can do, well, then you actually pass ownership to that resource, and now F may not know that this borrow refers to this resource. Then they become out of sync, and F may deallocate the resource before it has touched the borrow. So that would be unsafe. So you don't want that. Similarly, if you take an exclusive borrow and any other borrow at the same time, that's also a recipe for disaster, because here, similarly, you couldn't guarantee that this borrow here observes the resource consistently, because this operation here on the exclusive borrow could change things. However, if you have two shared borrows, like here in the last line, that would be okay. So they cannot really interfere. They are just two pointers, and they just do observations. So that is fine. Oops. Right. Last but not least, since borrows should be restricted to the lifetime of the object they are borrowed from, they must not escape from the scope that they are created in. At least that's our current view. I mean, you can be more liberal about that, but that we didn't find a way of putting that together with type inference. So in our system, the rule is that borrows must not escape. So they have to stick to some lexical, sort of lexical scope. And in this case, that wouldn't be guaranteed, because here we are taking a pair of a borrow to this great handle here. Then we close, and then we return X. Well, now X would be available, the borrow would be available after the resource has been closed, so that would not be safe. So what do? Our system tries to infer a region in which the borrow is valid, in which the borrow can be used. And if we try to return the borrow out of that region, then the type checker will complain and we get this back. So in our system, we can, so in the implementation, we can explicitly write these regions. We have a heuristics that usually finds a good region. So most of the time, you don't have to write anything. If you want to be more discerning, you may have to explicitly specify the region, and then you get the error message. Right, so in this case, the type checker would complain that things don't work out. Well, I think I said all that. Now, the interesting thing is, of course, you can have several such regions nested inside one another. And then you talk about nesting levels, and now the a bit tricky technical issue in our system is that now you also have notions of unrestricted linear and affine types relative to that region here. I mean, everything can be done in that region, and everything, we can have closures over that and whatnot. So we also have those kinds relative to that region. And if we nest further, they can be relative to the nested regions and so other. So essentially, you get an arbitrary deep lattice where on one axis you have linear, affine, and unrestricted, and the other axis is really the nesting level of those regions. And it's really just the product of those two lattices, and that will be your lattice which you use in order to calculate kinds inside of that region. So that's not in the talk, but if you want details, you can see that in the paper, and all that is also inferred. Right. And here in the particular case, so that would be a region of index 1 and borrows of index 2, like this one here. They are not allowed to escape. That's what you can do. Right. Good. So this is everything together. So if you write down the API of the key value store, that's what you would have to declare. Namely, you would say, okay, I have the type for the linear resource, and then my find and add operations, they are essentially, okay, so they take find takes a shared borrow of kind k, and then it returns a function that sorry, sometimes speaks to me. I don't know why. Anyway, so the standard way of dealing with that is that the operations actually either take shared or exclusive borrows depending on whether or not they mutate the resource. And that way the API looks reasonably okay. Right. And here you can see that pretty much everything works as we just talked about here. So here we have exactly the region that we saw before. And you can also make that into a function. So here we have this great subject function that would capture the resource. And since it's a shared borrow, we can also this function, it's not restricted in any way, even though it captures the borrow, so we can use it a couple of times. You can also do partial applications. That's just works just the same. So the types work out in the same way. And as you can see, no type annotation. So all that is inferred with a sort of principal type. Yeah.
Why do you need the explicit ampersand? It seems like the type already says that the type of reference.
So the explicit. So you need the ampersand in order to distinguish between the resource or the borrow. So the type says you want the borrow, but you still, in the application, you have to determine what you actually pass.
Right.
So it has a different type. So this creates a type. You could argue that the conversion could be automatic, but you could also argue that for documentation for the programmer, it would be better to have the ampersands here.
Right.
We tended to the last one. Right. Good. And what was that saying? yeah, so there's nothing new here. Yeah, no type annotations. So these are the implicit regions that are introduced by our system, and you can see they are disjoint. Therefore, it's okay to have this borrow here and that borrow on the other line. Otherwise, that wouldn't be allowed. So, for example, if you were using two of those borrows, like the function call that we had before. So if you have two borrows as arguments in the same function call, well, they would be in the same lexical region, and that would be rejected by the type checker. Right, so I don't have any time left, right? Yeah, okay. Let's just skip over that. So the way the inference works is essentially the first step is running the heuristics to find the regions. Then we generate constraints. That's mostly standard. And then we just solve the constraints and extract the. So that's the overall mechanism is fairly standard. The internals, the constraints are a bit more involved because they also have to deal with the linearity, and I mean essentially they have to figure out what you're using linear and what kinds of things you need. Right, and then so there's a lot to say about the algorithm, but I'll leave that to the paper. Yeah, and what I should say, in this step, the first inference gives you horrendously complicated type schemes because of all the subkinding constraints that you've got. Yeah, so you have lots of type variables, lots of subkinding constraints, and then Gabriel has implemented every possible trick known from the literature in order to eliminate as many type variables and as many sub-kinding constraints as possible. Now, so that in the end you get something that is readable. Right. So that's the current state. So there's a prototype that you can play with. Everything I showed you in the paper that we just discussed in the talk works there. What we don't have is flow sensitivity or non-lexical regions, as people like to say. We don't have a story for that, still not. And we don't have a concurrency story, which would be really useful, and that's really something that shines. And in the paper, there are many examples, many interesting examples, and all of the examples are also available to play with. You can only type check, unfortunately, but it's still fun to play with. Right. Yeah. So the theory, I think I mentioned that in the beginning already. So that's all. Thank you for your attention.
So there was question during the talk. Maybe we have time for one quick question. Yeah.
You're going to take questions after you close the talk?
Yeah, that's a contradiction. Huh? So semantically, I should just sit down. Yeah, but it's okay. Did you have a question?
I don't have anyone.
Okay.
So could you speak a little bit about how it seems like your system has some linearity? Like, can you compare it to something like Rust? It seems like the type system is a lot simpler. I mean, like the annotations seem a lot simpler. So what can?
That's probably no question. So.
I think that's an extended question, but I'm happy to discuss that offline. I mean, I mentioned before that we have this philosophically different starting point, I would say, and we, I mean, all the single concepts are there in a sense, yeah. So you have also sort of mutable, immutable borrows, and you also have, through the regions, you also have a concept like the lifetimes. Yeah, what should you say? So I think we started from a different position with different philosophy. That's probably the best way of saying it.
Okay, let's thank Peter again.